Hi everyone, my name is James, and today we're going to be solving the first order dynamics of a cup of coffee. Let's get started. The temperature of my coffee has first order dynamics, and it cools according to Newton's law of cooling, given by this formula up here, which says that the temperature of the coffee changes with time according to some constant K multiplied by this T infinity term is what we'd call the steady state value of the coffee, and this is what we would expect the temperature of the coffee to be after an unlimited set of time, or just a very long set of time. And from that we subtract the actual temperature of the coffee at some given point in time, and we're missing the closing bracket just there on the right. And now we have a little bit of extra information, and that is, suppose the coffee is currently at 50 degrees Celsius. And the room that the coffee is in is at 23 degrees Celsius. And we're going to use this information later on when estimating this value K. And also, on top of that, we're going to estimate that after 5 minutes' time, the coffee will have cooled to 40 degrees Celsius. And given this information, we have two problems. We first want to solve for the temperature of the coffee at some given point in time. And then we want to estimate this coefficient K. Now, to get started with the first part of this problem, there's a couple of approaches we can use. If you think back to like a first order ODE class or something like that, you might have learnt several techniques. One of them might be something like separation of variables, or probably the easiest way, I think, would be to just guess the form of this T. And for a first order system, that's pretty reasonable. I mean, if we think what it means for the system to be first order, it means it's going to have an exponential decay or rise, but it can only really have permutations of this being first order, which means what we would expect is we would expect that our T of T, being first order here, must have exponential decay scaled by something, which we're just going to call some constant A. And we know the decay term is our K. And then this offset here is the only thing we need to include. And so when we generally guess the form of the solution, if you remember back to your first order ODE class, you should hopefully remember that we can guess a solution with this sort of form. And this is where it comes from. The B sort of accounts for the offset, and the K accounts for any other scaling. With the guessed form of this, we could substitute this straight into the formula up here, but you'll notice we have this term on the left. So we may as well take the derivative of this one here so that we can substitute that in as well. So let's say that T dot of T, and taking the derivative of this is a constant, so it goes to 0. And then here we have our minus Ka e to the minus kt, and that's just taking the derivative of the exponential term. So now that we have both of these, we'll substitute them back into our Newton's law of cooling that we were given. So the left-hand side is just this big T dot. So we have minus Ka e to the minus kt equals K times our steady state T, which we don't know yet, minus our big T of T. So A e to the minus kt. And then because we're subtracting this plus becomes a minus as well, because this would all be in brackets. And we can expand out and collect terms. If we actually look here at this middle term here, we notice that we get minus Kae, or exponential, to the power of our minus kt. But when we bring that across to the left, it would become a positive, and these two things would cancel. I might explicitly just show that though. Equals K to infinity minus Ka e to the minus kt minus KB, and we can now clearly see that these two terms cancel. So what we're left with is KB here. We can see the K's can also be cancelled. And so we see that our B term, so our constant which we didn't know, is the steady state value, or the temperature of our coffee after a long amount of time. And that's what we would expect. Like, it kind of meets our intuition here. We have this formula here for the temperature of the coffee, and we would expect that once this exponential term, if t goes to infinity, this would all go to 0, and the temperature of the coffee should be whatever our steady state value was, or that time we said the coffee would be at infinity. So this matches our intuition. So what we can do is, if we get rid of this B now, and we can replace it with our steady state value. Okay, and now for part 2, estimating the coefficients, this is all about using the information that we were given in our problem description. So I think the first thing we should probably try and figure out is what this A term is. So the most useful bit of information we have for figuring out what that term is this first bit they give us that says the temperature of the coffee is currently 50 degrees Celsius. That tells us that at time 0, so if we change this t to a 0 here, this exponential term e to the power of 0 is 1, so we get a plus t infinity is equal to 50. But we also know that the temperature of the room is 23 degrees Celsius. That means that the coffee has to eventually end up at that temperature. So we can substitute that in. And we see if we solve this by taking the 23 over to the right-hand side, our A is equal to 27. So we can substitute that back in up here. So our temperature at time t is equal to 27 e to the minus kt plus 23. And now we just need to solve for our k term. The last bit of information we are given says that in 5 minutes' time, the coffee will have cooled to 40 degrees. Now, the time we work with here is actually in seconds. So we actually need 5 times 60 in this case. So we are going to consider when t is equal to 300. So we know that at t of 300, this equation at 300 is equal to 40, and that's given to us. So we can take the 23 across, so we get 27 e to the minus k, 300 equal to 17. So this gives us e to the minus k, 300 equals 17 on 27. What is this? K then is equal to 1.54 times 10 to the minus 3, if I haven't made a mistake here. Yep, I believe that's right. So we can get this by just taking the natural log of both sides. So you do like ln this and this, and then you can bring terms out. So we've got our k, and so then if we substitute that back in, our final, well actually that's it solved. That's part 2 solved, but the final form of our temperature at time t would now look like, with all of the terms in, 27 e to the minus 1.54 times 10 to the minus 3 t plus 23. And so if our coffee actually does cool according to first order dynamics, then this equation is an accurate model for how it will cool in that room. And so using it, we can determine what the temperature of the coffee should be at any time, as long as it stays in that room and all of these assumptions were true. And that's everything there is for this problem.